So thank you very much for the invitation. I'm sorry for proposing a subject that probably is not well matching to the activity of mathematics of networks, but I'll try to explain. There'll be some, okay, the statistical background, but there's some modeling, and this modeling is of interest for networks, in particular for wireless networks. Okay, so these are my colleagues, student and co-advisor. It's often the bulk of the work is due to student who is very, very smart, much smarter than me, just try to asking questions and giving answers almost immediately. Okay, so there's this thing is, it's a physicist, but probably biologists also. They observe that the nature, if we somehow represent some patterns in the nature, but some set of points, like a point process in our case, a pattern, they have quite often this kind of configuration, kind of pattern. Okay, so a striking observation is that it's not a Poisson, and most of us, starting from myself, we dealt with Poisson models, Poisson this, Poisson that. But if it's not Poisson, then what? Okay, so but the nature is like that, and I think if you do some, we'll see there'll become kind of estimation at the end of this presentation, in the middle of this presentation. But I think we represent positions of the base stations in Paris or somewhere. Probably not be a Poisson, maybe not so regular like that, but there should be some degree of regularity. Or regularity is a good term. It's a good term. The term will be exponent of the hyperuniformity. I'll explain this. So it's kind of parameter that can tell us how, among other things, how close we are to the kind of Poisson, or we are close to lattice, where there is very regularity. Okay, so this is for Poisson, and then this is transparency, is supposed to show that there are a lot of activity among physicists, but also biologists, and there are many models. Some people create models, some people try to understand this regularity, this degree of regularity, not yet explained here. And the idea is if I dare to present this to present this work here, there might be some maybe collaboration, some continuation of this line of thoughts in the context of wireless networks, for example. But I didn't have time, neither collaborated. But there'll be some relations to Feng was presenting some regularization of networks. So this was kind of modeling. This is kind of nature is regulating something, but we do not construct this model. If we construct the model just to somehow mimic the nature, and we're interested in this kind of regularity of this regularization, if you prefer this term, of the work of Feng. Okay, so this is hyperuniformity. We'll do it for point processes, maybe more general, can consider hyperuniformity of structures. And then the basic assumption is something is regular, and in this case Poisson process is regular. If you take the points in the window, increase the window. So I'm not interested really in expected number of points. So mean, I don't care. Density, I don't care. It's the fluctuations I'm interested in. Okay, so if this point process with Poisson, then the variance, fluctuations for me, it's variance for this work, at least for some time, variance will grow at the same rate as the size of the window. Okay, so it will be in dimension D would be RD, the ball, right? D. So the Poisson, the fluctuations of variance of the number of points, okay, larger and larger window, fluctuations of more and more fluctuations, and Poisson, it grows like a volume of the window. This is due to the fact that there are a lot of independence, and then variance, it's created through, contributes from small pieces. They are independent. So it's kind of hand-waving argument should be R2D. But here we are interested in structures and point process for which this variance, this fluctuation grows slower than the volume of the window. Okay, O of volume of the window. That was what I said. For Poisson, it would be just this. Okay, so the first attempt to capture something more regular than Poisson, less fluctuations than Poisson. Yes.
There's something regular to understand the formula. There is a small r and a big R. Are they the same?
Yeah, sorry. It's always have this question. It's always this type, but I always forget after the presentation to me. Capital R. I'm sorry. It's, okay. If it's only this small type, but I'll be happy. Okay. So having armed with this kind of first attempt to capture the nature Poisson versus non-Poisson, I give you a challenge to tell me what kind of something behaves like a Poisson versus more regular than Poisson. So I mean, we don't have time to ask. You're not students, so I'm not professors. I'm not asking you questions, but I'm trying to say the first attempt is to say, yeah, this is regular. Okay, it looks like a lattice. There's some missing point, but should be lattice. Should be very regular. No, the argument is simple. It's a matter whether dot is white or black. If you inverse the colors, so all white will be absent, and I put this absent now, so you will have you'll have only these missing points. The missing points contribute to the variance in the same way as those that are present there, and they remove them in a binomial in the IAD way, so it behaves like asymptotically Poisson. So the first simple argument, no, this behaves like a Poisson. So it is not really the regularity that maybe we had thought in the very beginning, something different. Okay, now this or dot, again, might try because it looks like what we had before. Maybe this is more regular and this is like more Poisson. No, it's other way around. This is Gini point process, and that one is quite strongly regular in this term, so hyperuniform and to some degree. I will give this term of the degree. I don't have to go to all transparencies, so please stop me. I prefer to share the idea with you if you're interested in, rather than just going to equations. And this is what we call it mattern or random sequential absorption. We can put Poisson point process from Poisson, like a rain of Poisson points, and I put them too close to each other. I cannot remove it, so I will not accept it and keeping accepting them when they respecting some range of hardcore range. And this is this random sequential absorption, and this behaves like a Poisson, despite of this hardcore phenomenon. While they're very close to each other. Okay, so there's something different than regularity. They try to try to understand, just giving look at this thing. Now, what is this degree of this? Now we understand regularity is not a good thing. Let's call it hyperuniformity. So degree of hyperuniformity. What is that? What's this degree? Well, if we said that the variance should grow slower than the volume, so I put in the exponent some minus alpha positive, okay, and this they call it exponent of hyperuniformity. If we have point processes satisfying this thing, and we observe something like that. Indeed, we have, but up to from 0 to 1. So if alpha is 0, it's like a Poisson, all these random sequential absorption or lattice thinning. This is alpha equal to 0. Gini, okay, put it aside. Up to 1, we will observe these fluctuations, like counting the points. These fluctuations, I'll be able to come up with point processes showing this growth of variance degree d minus alpha up to 1. So in one day, let's put aside one dimension because always apart. In dimension 2 on the plane, okay, if you just look the fluctuations of the number of points, or variance number of points, they can grow at least at slower rate. I can get its dimension to 2, sorry, 2 minus 1. There's no way to observe growth of fluctuations slower than 1 dimension. So there are structures having exponent of hyperuniformity of alpha or 2 and beyond 2, yes. In that case, whatever alpha, there are point processes, you have to believe me, now that there are point processes for which this exponent of hyperuniformity, it's 1 and beyond 1, whatever the dimension, but whatever the alpha, this degree is beyond 1, if you are going to understand it just looking the number of points in the window, the fluctuations growth stops at this thing. We observe that this is not a volume order, this is a surface order. So the reason of the fact that this growth of variance, if I look at the number of points in the window, somehow the growth stops, even if the structure is more regular, more hyperuniform, this growth stops at this volume, surface order, because my experiment, my microscope, my tool, I would say in English, it's too crude. If I just count the number of points and I stop around the window, it is the fluctuations around the boundary, whatever the regularity, it is them that will create this kind of fluctuation. So observing a point, just counting the points just in the window, this boundary of the window inevitably pollutes my understanding of fluctuation of these structures. So that's not a good idea to understanding hyperuniformity beyond these something alpha between 1 and 2.
Purely deterministic grid case.
Purely the deterministic is very problematic because it's kind of periodic. You will have something like that. But yes, it will be this one log. For alpha including one lattice, taking some precautions, lattice might consider as alpha being infinity. So for the lattice and something like for the Ginibri, for example, it is this. With Ginibri, I'm just spoiling a bit. For Ginibri, for dimension 2, alpha is equal to 2. Okay, so the way of measuring these fluctuations, it's too crude. It's a boundary. The function is not smooth. The big thing is, I mean, a small observation is if I represent number of points as a kind of indicator of points divided by r and the ball 1 is the same as x in the ball of radius r. So in fact, I'm going variance of the sum of some function. Here it's terribly non-smooth indicator of point x. Okay, so this non-smoothness of that function that I took for which I understand the variance causes this kind of effect. When I replace this indicator, something like that, by a function, smooth function, Lipschitz, or I don't want to go into details, something smooth, okay, some smooth, exactly of x divided by r of that function, I hope be able to observe something for all alphas. And that is the case. Not proving here, but not very complicated to prove it. So if I replace, instead of being interested in the number of points and fluctuations, I take a smooth function, whatever it is, and it's a linear, statisticians call it it's a linear statistics of a point process, smooth linear statistics. Then the variance, there's no boundary because the function is smooth. And we reveal the whole, behavior of the point process regarding its hyperuniformity of this degree, if it is somehow related to the model. Okay. And here I have presented you long examples. This is related to Gini point process. Probably not simulated with the Gini, but it is of that flavor. There are more, more strong. I tend to use this term, but it's like more hyperuniform. These are Gaussian analytical functions. They're 4 degree. And this is like close to Poisson, because alpha being to 0 is Poisson, and this is something in the middle. It's called, physicists call this a weak. Weak is specific, okay? Between 0 and 1, they call it weak, and beyond 1, they call it strong hyperuniformity.
So I don't understand. So you are was d minus alpha, and so d minus alpha was the order.
Yes.
Right? And so if d is equal, this is 2, so the variance tends to 0?
Absolutely. 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 In the lattice, there is no variance, it's 0 already. And so this is like, to physicists, all this comes from the observation of physicists. These are like crystals. If lattice is a crystal, there's no fluctuations. If you put some small perturbations, things like that, they become a small scale, might be very non-regular, non kind of Poisson, but at the macroscopic scale, this is really like a crystal. Yes, indeed. It's a legitimate way of thinking that lattice, hexagonal or whatever, alpha would be infinity, except that it's kind of, there's no Poisson. The way I'm going to define this alpha in a better way, this escapes this definition. Lattice escapes from this definition because, again, it's not regular because of there's no probability there.
I think you smooth. I mean, the things that were earlier with the boundary problem being problematic for the periodic case vanishing, right?
Absolutely.
Then,
Absolutely. For the lattice, for Gini-Bri, it's on the edge. For the dimension 2, Gini-Bri it's 2. So all these fluctuations, this thing, it's constant. Variance is 0,1. It's bounded. For Gaussian analytical functions, they somehow asymptotically, no normalization. I have already some kind of low numbers. As variance goes to 0. And if you want to have a central limit theorem, something fluctuations, Gaussian fluctuation, you have to boost thing because itself it goes to constant. Okay. Now here's maybe this is the part that might be of interest for us in the context of wireless. So say a prototype, a way of producing hyperuniform point process with degree between alpha equal to 0. That's Poisson, we know how to do it. Up to 2, there's an easy way to do it. How do we do this? You start from something with alpha bigger than 2. For example, Gaussian analytic function, that is complicated. Why not taking alpha all the infinity? So I start with a lattice like that, and I'm going to, in a controlled way, I decrease this hyperuniformity up to alpha between 0 and 2. It's possible. How to do this? Well, this is the lattice. I want to make it stationary, so that's a usual thing. I just translate everybody with the common uniform random variable. So forget about that. That's not very important here. Then individually, in an independent way, I'm going to displace them. I'm displace them with a random variable that is, if this random variable has variance, I'm getting alpha equal to 2. What does it mean, variance? You have to think of the family of stable random variables. Stable random variables are parameterized between 0 and 2. stable with parameter being 2, it's like a Gaussian, have 2 moments. In between 1 and 2, the first mean, but not yet variance, and in between 0 and 1, not even a variance. So I'm going to displacing this lattice basically far away. If I replace not far away meaning my stable being like a Gaussian. If I take a Gaussian fluctuations like a stable with parameter alpha, but I'm not displaced. It's not a mean, it's a variance. I'm not really heating it too much, and then all of this is heating. I'm taking lattice down to this thing. So it's like a way to produce something that behaves like in this hyperuniformity degree. It behaves like a Gaussian, like a Gini kind of way of calculating, easily produce something that behaves in terms of this hyperuniformity like a Gini, which is not easy to simulate, by the way. Now, if I take on the other side, if I take a stable random variable with having no even expected value, so that is stable having parameter close to 0. Okay, if I take a stable with this parameter, meaning that it has moments of up to alpha, in 0 and alpha, but no beyond. Okay, this means in practice that this lattice that I'm taking initial, I'm hitting at to this extent that I'm sending very, very far away. That's my understanding. Displacing with random variable, not having a mean, having only very small moment, it means I'm sending it very, very far away. Now, what's happening if I send them very, very far away? I'm losing completely geometry. At the end of this construction, my model, this lattice completely lost its geometry. It should be like a Erdős-Rényi. Geometry doesn't care. So when alpha goes to 0, meaning I'm sending very, very far away, I'm getting close to Poisson. Okay, so taking stable random variables parameter alpha close to 0, I'm perturbing lattice to such a way that it behaves at the end like a Poisson. And in the middle, I can keep some kind of regularity, hyperuniformity of lattice through this displacement, and then I get this thing. So it's kind of way of interpolating in between Poisson to sort Gini, taking lattice and sending it very close with Gini, stronger and stronger, hitting it more and more. I'm going down to Poisson. Okay. The way of all dimensions. It's all dimensions. Absolutely. Yes.
But the principle works, right?
Absolutely.
Of at least everything.
Absolutely. It's a matter of alpha and whatever the dimension. No, that's it. It's dimensions B. Okay. So now we have to revisit again this definition of this alpha, because somehow I was thinking this exponent of something of these functions. Okay. All of a sudden it's defined through this. Alpha should be such that for all smooth functions, this behaves like that. Is that true that all functions have this thing? Maybe from one function, different functions, all smooth, it's a different alpha. So alpha should be somehow kind of fundamental definition and not to function unless I prove that for all functions, which I'm going to do. Okay, so this is now, you have to go, fluctuations, it's a matter of spectrum. Spectrum, it's close to Fourier, so there are tools for Fourier. I'm not going to go, it's a nice relation to it. I'm going to just bring the Bartlett spectrum, which is kind of, for experts, no, Bartlett spectrum is well known for this series, time series or functions. Here it's for discrete point process, process. So the way of understanding is this. I take the pair correlation function. Pair correlation function, I think it's easy to understand. So it's a second moment correlation, second correlation, the expected number of points having at the dx times at the dy, two things. It's a second order correlation function. Okay, it's this thing. Okay, if my process is okay, all my models are here, the translation invariant. So in fact, this thing, it's just a function of the distance between these two locations. I'm going to use at these things. Okay, that's related to intensity. I don't care. This is just the distance that I observe correlation function between these two things. So I take this function, it's a deterministic function. Okay, I take the Fourier transform. Okay, this function has usually something like that going to 1 or something to intensity. So not going to have it's not L1, L2. You're not going to Fourier transform it, but it's take it 0, then it behaves like that. I'll show you examples. Okay, take Fourier and bring back 1, and this is a spectrum. It's a Bartlett spectrum for point processes. Now, as for Fourier analysis of random variables, if I'm going to understand, I'm interested in some kind of fluctuations for variance when the frequency. So it's quite easy to understand that I'm really interested in behavior of this Fourier close to 0. Fluctuation at large scales. Because large scales, it's a abelian thing. It's related to the fluctuations of behavior of the function Fourier representation at the origin. Okay, and this function is meant to. It's really a tool, thanks to Bartlett and Pierre Bremont. Beautiful contribution in this thing, that it's meant to represent covariance, hence variance as well, of two linear statistics of the data. Okay, two functions, covariance. Okay, it's represented. It's kind of Campbell-Fourier theorem. You integrate with respect to this spectrum of the point process. In my case, I understand that there's a density of it, because it might be just a measure, not signed measure. Okay, here is density. I integrate Fourier transforms of these functions. Okay, so in particular, for the variance of the function has this representation. Okay, so I can now, what I'm going to interested in this, trying to see the behavior of these smooth functions, variance, and this something like that. I'm going to do it online on this kind of substitution, double substitution, to bring back this volume times something. If this something is of order constant, if r goes to infinity, that I'm getting only this volume fluctuations. That's a Poisson. Spoiling again the thing. For Poisson, this is just a constant. So that's a constant. This is a constant. So this is just volume. For all point processes for which this function somehow goes to a constant, because this is k divided by r, and n r to infinity. So this goes to 0, modulo regularity and things like that. If s at 0, it's not a constant, something positive, then this is the order of this thing like that. Now, when s of k goes to 0 with some rate, I'm able to bring back to understand the definition of this thing through this spectrum thing. Okay, so this is like a very quick resume that I was trying to explain. The definition of fundamental is kind of hyperuniformity defined through spectrum. Hyperuniform point processes, it's non like Poisson, these are those for which the spectrum Bartlett at 0, it's 0. It means that that means that there are no energy in the very yes, as close to 0, meaning that the fluctuation at very low frequencies, the energy there's no energy in fluctuations at large scales. Okay, and now if by chance this function behaves like this, spectrum behaves like this, we call this exponent of the hyperuniformity. And for Poisson, alpha is equal to 0, as I said, it's a constant. Otherwise can be fundamentally can be in between 0 up to infinity, except that sometimes it's hard to cut examples to produce something alpha for, I don't know, 17 in dimension 2. Because lattice, perturbed lattice, I can only do in between 0 and 2, whatever the dimension. Okay, here is the this is this Fourier S of k without scaling of this Bartlett. So this is for Poisson. Poisson means there are fluctuations. Energy are carried by across all frequencies. It's like a Poisson point process, like it's a white noise in discrete world. White noise in discrete world. In discrete world, yes. That's somewhere Gini-Bri. So if it goes like 2 to a parabola here at the origin, this is something produced for perturbed lattices. Oh no, this is for one dimension. These are altogether whatever the dimension, because higher dimension in fact should be the frequency should be of the dimension of the point. So it's two-dimensional, should be two-dimensional frequency. But these are somehow, if they are rotational invariants, they can present it this way. Okay, and this is something that behaves like Poisson, not being Poisson. Thomas, it's a cluster point process on the other side. But there are point processes for which it goes even higher. I mean, the slope going to like that, infinity, like that. There are examples. Okay, so now very quickly, because I'm happy if you were, you know, understandable for this part. Now, estimation, there's not somebody who's not a statistician might not be very sensitive to this thing, but I'm just going to give you what we do. There's a state of art before we starting working on that. So what do the physicists and all the work? They first estimate this function, this density of the spectrum. There are discrete Fourier transforms. So it's the first approximation to estimate the whole function close to 0. And then you have to send on the estimator of that thing, you want to get the rate of that function through its estimator close to 0. So twice going to the limit, which is supposedly, presumably not so efficient. There should be a way to do it in an efficient way. Get an estimator not going through twice limits. This to the estimator and trying to understand the rate of this estimator. So now this all comes from the previous work on, it's a digression now, from the work with another previous student with Stefan Mella, that Stefan came up with this idea of capturing not only this kind of phenomena like fluctuations, but he wanted to capture the whole, everything, the distribution of the point process with this thing in the given window. Okay, and then he had this, descriptor through some bunch of wavelets, kind of linear estimators with linearity skilled, and this is, I mean, this kind of captures all quote phenomena of the point process, but there are absolutely no mathematical guarantees. Here we are back somehow, not going to understand the whole distribution of the realization of the point process. I just want to understand this part of that nature, meaning the hyperuniformity. For that thing, it is possible to do it. Again, there'll be some wavelets that appear. How to do this? So if we now understood this variance of these linear statistics, here I'm scaling through R to J. Okay, j, I'm going to take j smaller than 1. Somehow I'm scaling the function, the argument, the function, it's r a bit slower than 1 because I'm having a window, not have infinite. If I had infinite window, I could take j and I could come up with the same conclusion. But here, my estimator, it's in reality, it's a finite window. So the smooth function should be such that eventually, when r goes to infinity, this smooth function somehow I'm observed within the window and not beyond that thing. So that's why I'm scaling by something a bit smaller, bit between 0 and 1, than the window. The window grows, so I'm pushing the points to this window, but in the rate a bit. So some sense. Eventually, all the points will be pushing to that window. Well, right here, j. If I put j here and j here, I will get the same way. There's difference between here. Here is r to j. Here is r. So the result is the same, except that instead of, d minus j, I should be with I. If I take the whole infinite window with j1 or whatever, I would get thing. For the window, I need this j smaller than 1, and then rate is this behaves something like that. So asymptotically, if I take window larger and larger, okay, then this thing behaves like what? This is a constant. This is r of something exponent involving alpha. So I take the logarithm, yet not. If I take the function that is centered, so an expected value, integral point process is uniform, it's stationary, so integral of that function is centered, so integral of that function is 0. Variance is related to the square of that, because the mean asymptotically is 0. If my function is centered, this behaves like basically asymptotically expected value of that. Okay. Okay. Should behave like this times a constant. Well, constant depends on r, because it's only asymptotically when r goes to infinity. Otherwise for r, it's just something depends on r. Now if I put logarithm on both sides and divide by log of r, this will be this divided by log of r, and I'm getting access in the linear way to alpha. It's done here. Okay. So if I window, I take this my linear statistics, I take square of it, log of that, divide by log, I'm getting something like that. When r goes to infinity, this goes to 0 modulo that this does not go to 0. That might be a problem of error being too small in some sense, but otherwise I'm getting something like that. And now if I somehow simple linear observation, I'm getting a prototype of the estimator of r. So it's like a linear. If I go to logarithm, like a linear regression kind of alpha. Skip details to providing guarantees for this to work. I'm just showing you. It will be just at most 2 transparencies, and I'll be done. I understand that time is it's 15 minutes. Okay. I know it's. By the way, what's the usual to? Okay. Okay. So I'm not going to absolutely to set the transparency. So here is this estimator that I understood it in somehow in a simple way. If I take a function, if I this rate at which I'm going slowing a little bit, increasing but slower with the window, just to get information basically asymptotically in the window, I'm getting something related to alpha. I can somehow solve this. Okay, divided by getting. So it's a prototype of estimator because why? It's terribly variable. it's a random. This is random variable, so this is a random variable. So it'll be fluctuating a lot. What do people do if you have somehow estimate with the data? Usually, the classical thing is just like bring me another point process. I'm the same thing and the same thing and the same thing, and take law of large numbers to get estimated this value. Okay, but the goal here is not to ask for another realization of the point process, maybe not have it. We are going to find this diversity just within one realization. What I'm getting, why I can make this random variable converging to something, how I make it converging to, where is the law of large numbers? The law of large numbers somehow will come from having not different realizations, but different functions. This in this world, people call it tuppers. These are really wavelets. And eventually, if we like, at different scales, these slopes, because still it's free, a parameter of that thing. Okay, so if I altogether estimate, it looks like that. If you are interested in several slopes, different functions, what I explained, for the statistician, somebody who like Gabriel, for the statistician is multi-linear regression, they update this. Okay, so okay, it is this. There's some weighting, something like that, because there are different rates. So, but basically, it's kind of law. I'm going to rely on law of large numbers through different functions and different rates. Separated something like that because these are, rate depends on J. So statisticians tell that something like that. Now,
other than taking different regions of space,
because this is more efficient.
It's more efficient.
Yes.
To the function.
Yes, because you have chopping this thing, some organizing things like that. Is more. We'll see. I mean, I'll try to explain. So there are two transparencies, and then there are, there's a theorem. There are confidence intervals, but that's kind of cuisine interne, which is it's very I think instructive. So as I said, as we said, I get a bunch of functions. I take only one rate, this slope. We should think about something that I'm going when whatever R theoretically should go to infinity. I have R at most, it's my size of my window. So in fact, I'm not going to rely on R going to infinity. I take large R, large of my window. And inside, as we said, you can take different slopes. So in fact, in this window, I have this window. I can consider some rate of. I'm going to, increasing the frequency, lowering the frequency, jumping in the slope of the increase of understanding these fluctuations at different slopes. J, it's a bunch of them. Okay. I'm decide which one. One slope is enough, at least two, because I'm going to have linear regressions, so two of them. But then I have a lot of functions. I'm skip this thing. That's also understanding why should be not too much, not too many, but not too small. Take a Gini point process. It's just really realization that we do. Take a bunch of functions. They are these Hermitian wavelets. Okay, and then I calculate this function. One realization for this one. I take this value for the parameter as an argument J. So J is very small, bigger, up to 1. I told you J I cannot go beyond because this fails. The theorem says that I'm going basically it's a curse of the boundary that will hit me. So I'm free to take J's from here to there. Now, if I take some number of values here, very small, that means that I'm understanding these fluctuations at the rate very small. So basically, if J is close to 0, basically it does not decrease, almost constant. So in fact, I'm not doing anything. Okay, whatever the R, if J is very small, but a given R, given minus R, it doesn't tell me anything. Okay. Now, if I decide to slope as something like that, I get something like that. It's a kind of slope, but it is not the one that I'm happy to observe, because we know that the Virginia-Bree point process, the parameter is always 2. So these, solving this thing, in my function with respect to J, I should somewhere plateau like that, because this kind of figure. So indeed, it's not surprised that it's the last kind of phenomenon that you observe before 1. Usually would like to go, at 1 you cannot do. So just before 1, and do some, new practical suggestions how to find it, but it's very, very evident. It's kind of plateau, which is really of interest that you should take here for J, in this thing. Not too small, because it does not carry any information. This might carry information about the fluctuations, some not ultimate fluctuations. It's only here that we get. It is this. Now I take it.
There are no confidence interval in this.
There are transparencies, but I will just very. Okay. Now, I just want to say that it's kind of surprisingly efficient with respect to statistics. So physicists do as well. Now I go to random sequential absorption. Visual and if you try to compare this to that visually, hard to see anything. However, this the same function immediately. I mean, you get very, very evidently this last slope that you observe, it's close to 0. Alpha being 0, it means it looks like a Poisson. Okay, so it's quite efficient, and I have it's more easy to do it rather than patching this. In some sense, we do it because in this Hermitian functions, there are way of chopping to get functions, organizing them in the space, but you don't have to do it. It's a general way to do it, but it is here that you try to see the scale that is of a pertinent. Again, the theory is telling me that if I'm giving R, if you let me send R to infinity, even this would get the true slope. Okay. Theoretically, if I fixed J as small as you like, but I sent R to infinity, this will get like this. But it's only here that it's got this true. Okay, now theorem. This is a consistency of the estimator. As I said, it convergence in low to the assumptions. Sorry. Okay, so this estimator really goes to estimator. Again, remember, I'm not normalizing by anything. It's itself these things that I'm not going to time to prove. So there is like law of large numbers without normalization, I would say. And if you assume that the underlying point process is kind of ergodicity, here I took the strong assumption of Billinger ergodicity, but case by case, for example, Gaussian and also here, so since the argument goes through the Billinger, fundamentally I cannot go for alpha beyond D. So it is as if I were be able only to do it, not even for Virginia-Bree. But again, this is a general statement for the like a general assumption of Billinger mixing. But central limit, if somebody knows or proves the central limit theorem for linear functions, linear statistics, small linear statistics for a given point process, you can take it to understand, to estimate alpha. So for Ginibri it works, for Gaussian analytic function it works, but it's beyond this formulation of the theorem because I'm for those it's Ginibri, it's for d equal to 2 alpha it's 2, so I'm on the boundary, and for Gauss it's Gaussian analytic function is beyond. Okay. Probably the last observation. So why does it work? Why I'm going to be able to find this diversity in the law of large numbers with one realization and not having different realizations? The thing is that if you take these estimators, so these are terms, I'm coming back. Or maybe even here. Yes, there are these two. There is some different functions. I decided 10 functions and different rates. Okay, I'm asking, well, one realization. So this function, I'm taking different functions, I'm taking different slopes, but one realization should be terribly correlated. They do not give me diversity. Look, please. Theorem saying us that asymptotically, this multivariate central limit theorem, depending on slopes and frequencies, they're decorrelated. Different frequencies or different slopes in which I'm, understanding the phenomenon, they provide complementary information. As well as if that functions are orthogonal, they also provide complementary information. So I'm squeezing the information across different channels, and they are orthogonal in some sense. Well, careful. Orthogonal, for example, the Hermitian, they are orthogonal with respect to alpha equal to 2. So in fact, in Poisson, they are truly orthogonal. If I take for some alpha, if you take somehow craft the functions that are orthogonal with this kind of measure, but usually we do not know that, you cannot find the functions related to that thing. But despite of that thing, even if alpha is not equal to 0, they are not truly, if you take function, they are orthogonal with alpha equal to 2. For alpha reasonably not gigantic, they are close to orthogonality. So they provide a complementary thing. And these are confidence intervals. And then I'm not going to discuss because probably I don't have time to have the questions. If you ask the question, how many slopes and how many functions? Well, more slopes, better for you. Okay, it's close to 1. For the number of sorry. I'm telling lies. Okay, this is, forget about that thing. So if R is fixed, Bento is fixed for me. If I take more and more functions like Schwarz function, Hermitian functions, is better for me. As I said, they should be orthogonal, as many as them. Better these functions, better for the thing, but they are not really orthogonal. So no, to some extent, more and more it's better. It decreases the error. However, for a given R, to going to some number of too many of them, you capture the second phenomenon of the Bartlett spectrum. You are somehow polluted by the second order behavior of the Bartlett spectrum, if there is something like that beyond alpha. If it is very close to beta, be careful, not too many functions, because this term might hurt you, might decrease it. So somehow it's like a kind of trade. But this is, again, I'm not a statistician, but statistician telling us this is the usual framework for that be careful trying to decrease the variance. You might somehow miss the true value. examples. These are examples that I showed you, the perturbed lattices, and then these are confidence intervals, and there are data that are, somehow testify that we estimate something that we know because we produce through thing. And the very, very last thing. So these are we took that for the literature. These are biologists and physicists. They took it's a realization, it's a video, but I don't have to present it. They are small animals, something like appendix like that. They flow in the liquid thing. They do some turbulences, and these turbulences make them separated from each other in some sense. Okay, there are physical equations, but there are also statistical work. What kind of alpha, this hyperuniformity observed in this thing, and then in the literature they observe using the approach of state of the art through twice estimation of the spectrum and then going to zero. We said that this hyperuniformity should be O0. There are weak hyperuniformity between 0 and 1, 6. Okay, so we took this data and said, this data, no more than this data. Okay, and these do things. And then indeed what they observed, but this is something slope that it is here. But it's as if we're capturing some kind of fluctuations, but not the ultimate scale that we should be interested in. There's another one. We don't have to do interpretation. Why having these different slopes, except that, we observe them. And according to the theory, it is the last slope that appears here. It's telling that this is hyperuniformity of order 2, so stronger with respect to what they somehow conjectured. And that's, thank you for your attention. Conclusions, I think, 2 examples, maybe questions eventually.
Hello.
Oh.
There may be question online in the room, and
Okay. Okay.
Yeah, thank you so much, Bartek. It was very interesting, and I'm really wondering how does this impact the type of performance we get, like in the deployment of
yeah, so I take this a question, your question, try to ask maybe your question, because I hope to. So first thing is like, there are these perturbed lattices, which kind of very easy way we can perturb them. Now I understand theoretically how it works. Okay, it does not give a closed form analytical model, but gives a model you can use and somehow simulate on it or try some performance. What kind of performance I would be interested in, I don't know, all these kind of wireless things like that. We do it Poisson for Ginibri analytical approach, yes, but is this of interest to, if there is some, so the framework would be the same, the following. I observe something, the base stations of access to Wi-Fi access. They are as they are. I cannot change it. That's the nature. Okay. Now, usually, let's do it Poisson. Let's do that. Is this of interest to just really? Okay, what model? Why not taking perturbed lattice? Because why not thinking that people perturb them, like initially, and then but how do we do this? I take this perturbation with this parameter alpha. All of a sudden, I have a model, a legitimate model, theoretically having guarantee of having some fluctuations of the scales. Now, is this what kind of this behavior, this linear statistics, smooth linear statistics, they fluctuations are of interest? How to relate them to some QoS questions? I don't have a clear view, but that would be the thing. Would be a kind of, if we are not regulating, we're just getting something, and then we have the parameter, and the parameter fluctuations, some in a very simple way, simplistic maybe, should be related to the quality of service in some sense, usually more fluctuations. Probably there's a question of latency. Should be somewhere in this picture.
At some point you are saying you can go from lattice to any hyperuniform point process with alpha equal to, let's say, 2.
Up to 2, yes.
Up to 2. But between 0 and 2, right?
Yes.
But what do you mean by it is hard to go beyond 2?
Because there is no, the thing is that there are no random variables having stable parameter beta beyond 2. It's easy to understand. So look, if I'm going to, if I have a Fourier, I got it, maybe too late. But if you take a Fourier co-characteristic function of the random variable, okay. If you want to have this. Yes. Okay. So this is the Fourier transform, the characteristic function random variable. At 0 is always 1, so I subtract it, and now it should behave something like that. Now, if you want to go beyond alpha equal to 2, that would mean that the first term of the development is 0, meaning the mean has to be 0. That's not a problem. If I come at equal to 2, meaning I have the second term is of order 2, it's okay for me. I have variance. Now, if I want to alpha bigger epsilon alpha plus epsilon, meaning this random variable has mean 0, variance 0. So if I mean 0, whatever mean, and variance 0, it's a constant already. So beyond alpha, I'm jumping. I'm not moving at all. There is no. That's a nature of random variable. It's kind of Fourier fundamental domain of random variables. There are no them like that.
But it's possible that you start from a hyperuniform point process at an alpha.
It's always, you can always smooth it. There's no way to make it harder. The thing is, if you have, this is for then, suppose the underlying is of beta and alpha. If alpha is smaller than beta, you are somehow smoothing it up to Poisson. Okay, you can smooth it up to 2. But if it is already smaller than that, I'm not going to do anything. This is because of independent displacement. Feel free to construct point process with hyperuniform, starting from something, and you can make it, go up, but not independent displacement. And this is independent displacement. That's a fundamental assumption here. Thank you. Thank you very much.